Thank you for chiming in, Phoebe. Okay, today is going to be another exciting big day. We don't know why our warm-up is not working. One, everybody needs to sign up for their AP account. So first thing in the module, here's the link to the AP. You're just going to create an account and join with my join code, Swift down here, 2AWD44. Has anyone not been able to do this?
I couldn't do it because I got like an error code when I tried yesterday.
Okay, well, try it again. Again, the whole web has been having weird issues. Things have been appearing and disappearing out of my folders. So the idea that it's not working to be, oh, look, we got everybody. And yeah. Welcome, Juan and Priya. So we're just starting out. The warm-up does not seem to be functioning, so we're just going to quickly go over that and skip to something else. Signing up for your AP account. Ideally, everyone needs to be signed up by the end of this week. It only sounds like one person is having trouble, but I think others might be too. This is the link to the AP website. It should be just ap.org basically. When you go in there, you're going to create your student account and you're going to use my join code, 2AWD44, to make sure you're in my section. You might be having to say whether or not you want to take the test. I don't think so at this point. There's nothing bad happens to you from taking the test. If you get a 1, so be it. If you get a 3, ideally you might be able to get credit for that in a college class. A 4 and a 5 should guarantee that you are able to exchange that AP credit for one of your requirements in college, which is pretty cool. I got a 3 in my biology AP and I was able to use it, but I did have to take an equivalency test. Okay, so back into the module. Yes.
It's temporarily unavailable.
Which?
The AP class thing.
AP link?
Yeah.
You can try going directly to the site. I literally just look up like ap.org. That's got to be the main site.
Yeah, I went to the site and it says it's temporarily unavailable. Okay.
It sounds like they're having trouble too. So try it tomorrow. I'll touch base on Monday. I don't think we're signing up everyone for something over the weekend. It's just they want to make sure that everybody's in with enough time to get any stragglers taken care of. So try that out. I would definitely wait half a day because it seems to be having real issues. Okay, so today's warm-up was supposed to be a multiple choice question. Which one of the following would, oh, hang on. I'm going to stop sharing so that you can't see the answers. And I am going to ask, although you've probably already seen them all already. Which of the following would result in a better digital approximation of an analog black and white image? Increasing the size of each sample square, thus decreasing the amount of samples taken. Decreasing the size of the sample square, thus increasing the amount of samples taken. Using decimal numbers to represent each pixel, or using fewer bits to represent the image. Which is going to give you a better approximation? He's been in here before. Yep. Hi, Alexander. Are you having trouble, or do you think it's the system? I was just checking to see if you got bounced out for any particular reason, Alexander. Okay, so you missed the question, but does anyone have an idea? Which would result in a better digital approximation of an analog black and white image? Think of our goose. Increasing the size of the pixels that we're using, the squares, decreasing the size of the squares that we're using to sample with, using decimal numbers to represent each pixel, or using fewer bits to represent each image. Poor thing.
Decreasing the size.
Who's that?
Donis. Decreasing the size of each pixel.
You are spot on. Or I should actually say, Who agrees with that? Come on, we're supposed to have a chorus of voices since I've said it's the right answer. There, Phoebe says yes. Yes, that is the right answer. Thank you for turning on cameras. Again, it's much more fun for me to see everyone. Okay, let's go to 2. So why is that? We will create a better digital approximation of an analog image when we use smaller sampling sizes. We use a finer grid to represent that image. That's what it's saying. Bigger sampling size or bigger squares, it's going to be more blocky. Smaller sizes, it's going to be more smooth. And we're going to skip this one and we're going to go straight into the presentation, which is going to have a, let's watch the video to start with, and then we'll get into it. So if everyone can go into code.org, or actually I can present it, but this is going to be, today we're going to be doing, well, let me go to the presentation. Okay. Oh, so just FYI, everyone who's in here, if you open up your presentation that's in your module, okay, the editing color images presentation, if you can go to that, you want to be in slide 6. You probably have to have it in present mode. Click this link to P2 slide, and that will drop you into this slide that you can edit. And I want you to add the logos that you decided to do, and then we'll get to review them. So that's something you can be doing while we are proceeding. So this is our video. Let me present.
Hi, my name is Lamora Free, and I'm an engineer here at Adafruit Industries.
Your screen.
And this is where I do engineering.
Yeah, you didn't share your screen.
Circuits.
Hang on, what?
We
Are you
can't.
not-
You didn't share your screen.
Okay, no, I did. It's supposed to be, the problem is it's not popping in. Hold on. Here we go. You don't need visuals. You know all this stuff. Thank you. Again, I apologize. It's so hard to tell which is doing what. All right, so we're sharing, we are reducing, come on. No, I don't want that. I want you. Okay, here, let me stand up. That won't work. Share screen. Here we go. Okay, are you seeing the full picture video?
Yeah.
Seeing. Okay, so let's.
Hi, my name is Lamora Free, and I'm an engineer here at Adafruit Industries. And this is where I do engineering and design, and I design circuits for fashion and music and technology.
My name is Federico Gomez Suarez, and I'm a software developer with Microsoft Hack for Good. And I look into using technology to help us solve some of the big social problems of our times.
You may have heard that computers work on ones and zeros. Or you may have seen scary looking visuals like this. But almost nobody today actually deals directly with these ones and zeros. But ones and zeros do play a big role in how computers work on the inside.
Inside a computer are electric wires and circuits that carry all the information in a computer. How do you store or represent information using electricity?
Well, if you have a single wire with electricity flowing through it, the signal can either be on or off. That's not a lot of choices, but it's a really important start. With one wire, we can represent a yes or a no, true or false, a 1 or a 0, or anything else with only 2 options. This on-off state of a single wire is called a bit, and it's the smallest piece of information a computer can store. If you use more wires, you get more bits. More ones and zeros with more bits, you can represent more complex information. But to understand that, we need to learn about something called the binary number system.
In the decimal number system, we have 10 digits from 0 to 9, and that's how we've all learned to count. In the binary number system, we only have 2 digits, 0 and 1. With these 2 digits, we can count up to any number. Here's how this works. In the decimal number system we're all used to, each position in a number has a different value. There's the 1 position, the 10 position, the 100 position, and so on. For example, a 9 in the 100 position is a 900. In binary, each position also carries a value, but instead of multiplying by 10 each time, we multiply by 2. So there's the 1's position, the 2's position, the 4's position, the 8th position, and so on. For example, the number 9 in binary is 1001. To calculate the value, we add 1 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1. Almost nobody does this math because computers do it for us. What's important is that any number can be represented with only ones and zeros, or by a bunch of wires that are on or off. The more wires you use, the larger the numbers you can store.
With 8 wires, you can store numbers between 0 and 255. That's 8 ones. With just 32 wires, you can store all the way from 0 to over 4 billion. Using the binary number system, you can represent any number you like. But what about other types of information, like text, images, or sound? It turns out that all these things can also be represented with numbers. Think of all the letters in the alphabet. You could assign a number to each letter. A could be 1, B could be 2, and so on. You can then represent any word or paragraph as a sequence of numbers. And as we saw, these numbers can be stored as on or off electrical signals. Every word you see on every web page on your phone is represented using a system like this. Now, let's consider photos, videos, and all the graphics you see on a screen. All of these images are made out of teeny dots called pixels, and each pixel has a color. Each of the colors can be represented with numbers. When you consider that a typical image has millions of these pixels, and a typical video shows 30 images per second, and we're talking about a lot of data here.
Every sound is basically a series of vibrations in the air. Vibrations can be represented graphically as a waveform. Any point on this waveform can be represented by a number. And this way, any sound can be broken down into a series of numbers. If you want higher quality sound, you would pick 32-bit audio over 8-bit audio. More bits means a higher range of numbers.
When you use a computer to write code or make your own app, you're not dealing directly with these ones and zeros, but you will be dealing with images or sound or video. So if you want to understand how computers work on the inside, it all comes down to these simple ones and zeros and the electrical signals in the circuits behind them. They are the backbone of how all computers input, store, process, and output information.
Okay. Let's get out of that. Let's cancel you. Come on. All right. Let's go to the presentation for the day. Let's see. Now here's a question. Are you seeing my presentation now?
Not in
slide-
full screen mode, but we could see it.
Okay, no, but it's, I have it in full screen. So hang on. So yes, I've got
Yeah,
it.
we can't see it.
I don't know why it does this. It just doesn't. It doesn't handle these windows that pop out well. Okay, so now you can see this, correct? Are you seeing in full screen?
No.
No. That's weird. Stop sharing. Let's start sharing on the new window. Okay, here we go. Yeah, so we're still having the issue that when I go to present, it's popping it out in a window that it's not tracking. Okay, so we had a little bit of our warm up. We had our video helping us to orient to where we're going today. Today we are going to be working in color. Yes, last class we were working with black and white images in that pixel widget. Anyone have any questions about last time? Any issues with the homework? Any issues creating your logo? That's what I like to hear, but I'm always worried that there are questions. You can use, oh shoot, of course, now I'm, hang on. Somehow the chat disappeared.
Wait, I have a quick question.
Yes.
For the black and white images, it's due Friday or today?
Black and white images ideally were due today. Friday will be fine. Don't
Okay.
worry if you haven't turned them in. All we're going to be doing right now is taking a look at some of the fabulous pieces that we created.
Okay, thank
Okay?
you.
No problem. So due today is our warm-up that we couldn't do, but we did in class. I will mark everyone accordingly that we've done it. There is an exit card at the end that you need to do, which is ideally done today. And black and white images is due today. Color images worksheet. I am not sure why that is in here. I don't think that we're probably going to get to the end of it today. So that doesn't make sense to say it's due today, but it will be due, say, next Monday. So you'll have till next class. Our goal is that you will be able to explain how bits can be used to represent individual pixels of a color image and how digital data is used to approximate real-world analog data. Okay, does everyone, this is going to be a major theme, the difference between digital data and analog data. Can anyone explain for me what analog data is? Team, can we ask someone? Hang on. I'm going to pick someone. Let's see. Ryan Weiner, do you have any idea what analog data is versus digital data?
I'm assuming analog data is something that's written down, or not something, not like computer data store, like is like
That's anything basically that has not been digitized. So it's a painting, it's a song played off a record. It's a song that you hear in a live performance. What that means is in analog music, the curve is totally smooth. The way the notes transition one to the next is seamless. It's like a straight line, where when you recreate that straight line of music, the curve, digitally, you are creating an approximation of that line with pixels, basically, that you're doing it in individual stair steps going up and down. You can make them very small, which makes them very smooth, but they are still on or off. It's not a smooth curve. It is a curve built out of pixels, which are going to be little, digital bumps. Okay, let's keep moving on. But that is a very fundamental idea that we're going to be toying with today. Now we seem to have lost our mouse. There we are. Okay, here's a fun one. In theory, you guys should be able to, if you open up your presentation, you can place these pins. Well, that's sad. I swear it worked in rehearsal.
It doesn't matter. It says view only.
I hear you. I swear I was able to do this. Anyway, let's do it by, I should actually poll, but the question is, how do you feel about this idea and your familiarity with binary, the difference between binary and decimal numbers, how we're using binary to represent information in a computer world. Ideally, I think most people are getting it, but does anybody feel that they're in this struggling category? You can privately text me if you want. All I'm saying is basically, is everyone okay with where they are? Do you feel, I mean, I don't think that everyone gets it at this point, but hopefully we're making progress. If you're struggling, it just doesn't make any sense to you. I think everything I've seen so far, it's making sense to most of us, but if you're having a real problem, you can privately chat with me and we can talk about this later. But this is just trying to get an indicator of how we're doing. Okay, so where is my control? There. So lesson 1, or unit 1, lesson 8, color images. Here we are. Why is The Wizard of Oz here? The Wizard of Oz was the first movie that ever got Technicolor. It was the first color movie. So that was very exciting. All right, we've done that warm up. Oh, here's another warm up. I don't know why it doesn't seem to be going anywhere. This is our slide. And then, okay. So what we're gonna do now is we're gonna look at some of our work that we did last class. If you have not put your work up yet, if you put the presentation in present mode, you can click this slide and it will take you to our presentation. Let's go through a couple of these. Kenneth Gow. Can anybody tell me what logo this is? Come on.
Yeah.
It's Shrek.
It's Shrek. Great job. That is tough. That is a really nice job. Okay, let's go to the next one. Ooh, this is Alex Klein. Can anyone recognize that logo? I think I have an idea. Come on, does anybody have an idea? Just take a guess.
The Wi-Fi?
I think that's Wi-Fi. Alex, can you confirm for us that it's the 3 little signals going out?
Well, it was Spotify, but it's more circular and it's kind of like a pain to make, so I changed it to Wi-Fi.
Okay. And what's happening is you just have too big a grid. But if you used a finer grid, that might have helped us. Don't worry, it's all good. Okay, here's one. I don't recognize that, but it looks like an M to me. Anybody recognize this logo?
McDonald's.
What is it?
McDonald's.
McDonald's. There we go. Ryan, is that correct? Ryan Wiener?
He said yeah in the chat.
Okay, oh, there we go. If anyone is having problems with their microphone or anything, you can call in and video so that you can use your phone for the audio. Because I know that's been a problem for some people. Okay, this is Bora Barclay. I think I know what that is. Who else has an idea?
Facebook?
Looks like Facebook to me. Bora, can you confirm?
F.
It was the Fortnite logo.
Oh, Fortnite. Well, just goes to show we're not up on our logos. Again, this is a nice one because it's very simply represented, but part of that problem is once you have an F, is it Fortnite? Is it, I'm not sure, because analog logo in a digital world. Ooh, look at this. Okay, does anyone recognize this logo? Anybody? Sabine, do you want to tell us? I think that it's like
It's Mojang.
What's that?
Mojang. I think it's Mojang, like the company.
Yeah, it made Minecraft. Company that made Minecraft.
Oh, cool.
Yeah, it's the Mojang logo.
That's okay.
That's the old Mojang logo. They have a new logo. The new logo is better.
Yeah.
but it's the words, so it's hard to do.
There you go. Well, great job on that one. I didn't recognize that. Okay, here we go. I think I know what this is. Somebody else want to guess?
Google is? Google.
I'm thinking Google.
I'm
May?
thinking Gatorade.
Oh, Gatorade. There's one.
It's Google.
It's Google.
No, it's Gatorade.
No. Well, again, that's the beauty of when we use a big sample size, it covers a world because you just can't represent it that finely. Okay, I think we got the hang of that. Great job, team. Really cool. That makes me very happy and excited to see all those. All right, let's move our way down here. Okay. Let's go into present, and then I'm going to have to probably bail out and get back in. The screen has stopped sharing. Oh, come on. You're not going to do this to me again. I've got to present this. Oh, but I can't do that, can I? Oh, yes, I can. Come on. Where's my share screen? Aha! I forced it into submission.
We can't see your screen. Oh, now we can see your. We can see your screen now. Never mind. We can see it.
Okay. Donna, I swear I did the 6 steps apparently to make it so that you could. Okay. This is just going to be in the chat, or you can shout them out. How many different shades of the color blue can you? Why not let's put them into the chat, and I'll start calling them out. We've got blue, blue, indigo blue, sky blue, navy blue, baby blue, light blue, turquoise, teal. Is teal blue? I always see it as green. Ocean blue, blueberry blue. Those are awesome. Neon blue. The question is, can a computer represent all these colors? What do you think? Can your
Yes.
computer that you're working with represent them all?
Yes.
I think it depends on your graphic card. But typically there's always going to be a limit on how many colors your computer can produce, unless you've got something fantastic. Just for like in the video, you've probably got 48 billion colors, or the ability to produce 48 billion colors in your machine, which is pretty much every color that you've ever seen. But the idea that in an analog world, there is an infinite amount of colors between one part, the start of the blue band and the end of the blue band. No, you can keep splicing it finer and finer. In digital, it's one or the other. It is either, blue, blue, glue, blue, hang on, or neon blue, or blueberry blue, or ocean blue. It will never be anything in between because it's digital. It can only do one thing. So once you create 24 billion and one colors, you've gone past your machine's ability to store it. Okay, let's get today we will be working in, I hate to do this, but go to code.org and we're going to be working in Unit 1, Lesson 8. This is going to be the worksheet that you're going to work off of. I would think you should make a copy of it. So just go File, Make Copy. So this is going to be our activity guide for today's encoding color images. We're going to practice with the pixelation tool. We're going to use the pixelation widget to recreate specific colors. We're going to recreate simple color images and describe the difference between using 6 or 12 bits per pixel to encode. Oh, that is so interesting. This sheet is out of date. So I'm going to go in with you into code.org and I'll show you. It's basically, we're just going to start on lesson 2 in lesson 8, or part 2 of lesson 8. We already did part 1, which was to look at the video. Okay, so I'm going to hop out of here because this is a little confusing. This is saying find the lesson in Code Studio Unit 2, Lesson 4. This is from last year's presentation. Don't ask me why they didn't update it. But basically, it's going to be the same task. Everything is the same. It's just these numbers are off. The task below, follow the guided sequence in Code Studio, which has tutorial videos followed by specific tasks. The purpose of this activity is only to become familiar with the color pixelation tool and to practice a little bit in order to be comfortable enough to start the favicon assignment. My gosh, that's a great term. So step 1, 3-bit color. How do you use the pixelation widget to control color? Okay, so let me go. Are you still looking at my full presentation? Yes, you are. Hang on, let me get out of here and get back in with what I'm looking at now. Okay, so now I have, this is code.org. I've gone in, I've gone down to lesson 8. We've already done the lesson overview. That's our how computers work, data and binary. Now we're going to RGB color. Okay? RGB color means red, green, and blue. Red, green, and blue are the primary colors that your television, any computer, uses to create its imagery. There are actually different systems than RGB, but RGB is a classic standard. Last lesson, we used 1 bit for each pixel. That meant we had only 2 choices for each. Off was black, on was white. We were turning on the light, the white light. Today, RGB. How many bits do we think RGB has? Come on, you can read the...
6 bits.
No!
3 bits. 3 bits.
3 bits. Red, green, and blue are each going to be represented by a single bit. And this is just for this next lesson. You can use more, but for this lesson, so you're going to have, instead of a single digit number, 0 and 1, you're going to have a 3-digit number, but it's still binary. So if you go to 1, in your 3 digits, you're going to get red. The second number is going to be green. If I turn this on, it's going to be red and green, and it's going to be produce what? Blue. No, it's not. It's not what blue is. What is red and green? I can't remember. The last one's blue. So if red is 0 and blue is 0 and green is 1, it'll be green. If red and green are 0 and 1, blue 1 is here, that will be blue. That's the 3 bits. We will have 8 choices of color for each pixel. Let's see what you can make all 8 colors in the next level. Okay, so we're into part 3. Color pixelation task. Can you make all 8 unique colors using 3 colors, 3 bits per color? We've done the first 2 for you by turning on 1 bit at a time. I think you need to do this in your worksheet, not on the code.org. If not, if that doesn't work, do it in the code.org studio and then transfer what you do for your coding onto your worksheet. Can you tell which is going to work for you? I apologize that I don't know. Is the worksheet active?
No, I don't think so. You can't.
I don't think so either. So go into your code.org, and this is where you'll do the work. And I would think that should do it, but I think that they want you to transfer it to that worksheet. So it would just be, once you do your stuff, why are those in there? You're just going to copy this line and then drop it onto your, drop whatever you do for work, copy that and drop it into your worksheet. Does that make sense? Okay, so everybody, let's take 2-3 minutes and try and get this done. Let me know if you're having problems. Oh shoot, that's a question. I think, hang on. I am going to break you out into breakout rooms, and you're supposed to have a partner to do this. Some of you might have 3, but you're basically just going to try and do the exercise, but you'll be together so that you can advise each other if it's not working. Okay? Does that make sense? Okay. All right. So let me know, has everybody already done this? Do we want to do the breakouts for this one or the next one? Has anybody not finished this?
I haven't done it. I'm kind of confused. Are we just,
Let me put everyone in breakout rooms. We'll take 3 minutes, take a look, and we'll figure it out, okay? So you can talk with the person in the breakout room to help you figure out what you're doing wrong or how to get it to work. So basically, the idea is we have a 2x4 pixel box, 3 bits per pixel. These are the representations for red, green, blue, and turquoise. Red is the 1. The 1 controls the red. 1 in the middle controls green. 1 at the end is blue. When you start combining them, when you put blue and green together, you're getting that light blue. So you're just trying to create 4 more colors down here using only these binary numbers. In you go. We'll come out about 57.
Do you want us to put this into like the readable format or just one long line?
I think it's easier to understand in the readable format, but you can do whatever you want because I can always shift it from raw to readable.
Okay. And do the colors have to be in a certain order?
Do the what? No.
Colors
All you're trying to do is create 8 different colors.
Okay, thank you.
Can you make all 8 unique colors using 3 bits? Richard, is there a problem?
Oh no, I just finished the thing.
Are you not being invited into a room?
No, I forgot. I Mr. Swift, you're muted.
Don't worry, I'm just muttering about the state of sharing these days. It just keeps taking away all my stuff. Okay, so how did that work? Was everybody able to accomplish the goal of creating 8 different colors using the 3-bit color pixel machine? Was anyone not able to finish section 3? Okay, come on, be brave. You can say so. You can chat with me. Sorry, the chat has been acting weird and it like took away my ability to private chat. So I apologize for that. Okay, if everybody's fine, we're gonna move on. We're moving on to 4 more shades of color. Okay, so now let's use 2 bits to control each color of light. This will be 6 bits total for each color. So now you have 2 bits per red. So it can be 0, it can be 1, it can be 1 0, 0 1, 1 1. Those are going to give you your different colors. So 0 0 is sort of a black red. Well, actually, apparently it's black. Red 1 is dark red. 1 0 is a plain red pixel, and 1 1 is bright red. Okay. When we hit continue, okay. Puzzle 5 out of 10. This time we'll use 2 bits for each color channel, which means 6 bits per pixel. We've done all the shades of red for you in the first row, and now you will follow a similar pattern to do the same, to do the shades of red, of green and blue in the last 2 rows. Okay? Hang on, close your eyes. For some reason, stuff keeps getting in here. Okay, so this should be what you're starting with. Again, I'm going to split everyone out into the rooms. Let's take another 3 minutes to do this. If you're having problems when you get back, we'll figure it out. Okay, but it's pretty straightforward. Now you have 6. Your image width is 4. Its height is 3. You have 6 bits per pixel. Okay, in you go. Rooms are opening now. Is everyone okay? Anybody have any questions? I now look off to my right, to your left, because I have a second screen to try and monitor things. Okay, about 30 seconds and everyone will be back. Does this seem to make sense to you? Is it intuitive? Any feedback from anyone as to whether this was easy or hard?
Green was hard. Not that hard, but a little bit more challenging.
Right. No. It's the idea is it's supposed to be ramping you up slowly to figuring out these things. You know, of course, the next one's going to be even more complex. Okay, everyone's back in. Was anyone not able to make this work or couldn't figure out how to work with the 2-bit color? Okay. Again, you know, if you're worried, you can always text me that now the text seems to be working. We are going to hop back in and go to the next phase. Okay. So 6. Let's gain even more control using 3 bits per color. This time you have 9 bits per pixel. Again, we've done the red row for you. Your job is to complete the shades of green and blue. So you're just going to be doing the exact same thing, but now you have even more colors that you can make because you've got 3 bits per pixel. Okay, so there's the red row. You need to make the green row and the blue row. All right, we're going to break out again, let's say 3-4 minutes. So we'll be out at about 11:08 or so. In you go. Let me know if you have any questions. If you want to chat, text in the chat. So this is 8 wide and 3 high, 9 bits per pixel.
Mr. Swift, do we need to copy and paste this into the document? And then is this document due like tonight or tomorrow?
The document ideally is due by next class.
Okay, thank you.
Is my feeling. And I think as long as you do it all,
Okay. Thank you.
so I'm given a worksheet, so we should need it for some reason. When you fill in your stuff on the worksheet, does it change the colors in the window?
But it stays the same. I just copy and pasted mine.
I figured I'm just going to be looking at the code then. But I think as long as you finish your code.org, so you should be in your breakout room.
Yeah.
Guys, Parker, Sabine, Kenneth, you should be in your breakout rooms. And try and unmute and talk to people. About 10 seconds and everyone will be back. Okay, everyone's back. So the next one, so did that work for everyone? Did you understand how to make the 9-bit pixelation work to make your different colors?
Can you go over
Anybody
the,
not? What's that?
can you go over the green one real quick?
Okay, so green is going to be, let's see, 0, 0, 0, 1, 0, 0, 0, 0, right? So I've got a 1 in the greens. If I copy that and put it here, I can make 2 1s in green. I copy that, put it here. I can make 3 1s in green. Yep. That's 3 greens. Then we're going to go things like add a 0 in the greens. Let's go 0, 0, 0, 1. That should be a different green. You're just changing these arrangements every way you can to get green. Then you can also probably, I don't know if it's going to change the green. Let's say that we do our big green, one piece of red to it. See, that's a different green. That I can add, things like, you can make a blue green, let's say. Oh, that's what we've done. We've created a wrong. So I find that it does help to keep the readable format. Does that make sense to everyone? But that's one way that you can do it. Okay, we've got 2 minutes left in class. The next one, I want to make sure that everyone can do this before we leave class. It's saying more shades of color. Pick a section from one of the images below. Use sampling to match the color pattern as best you can using the widget on the next level. Okay, so if we continue that, then it goes to this. So I think this is what it's at. This is what you're supposed to be doing. The color pixelation task 2. Let's see if we can make the sampling from one piece of one of these images from the previous level. See, I don't understand where that's supposed to go because this is the only new widget and it only has 1 bar. So it's the idea that you're trying to create part of that. I'm not quite sure what this one is asking because it doesn't seem to link to a widget. It's like you have to go back to the old one and try and create something like that. I wouldn't worry about that. Then there's just going to be 2 checking for understanding and a reflection. Okay?
Excuse me. Is our homework, is it a document or is...
We need to finish this module and you need to turn this in by next class.
How do we turn in a module?
You've got the worksheet.
The worksheet. All right, I see.
The worksheet should be done. And I think as long as you're doing it in the module, code.org should be recording that.
Wait, so
but ideally, it's the idea that you downloaded that worksheet. So this guy. Step 2, 6-bit color. Step 3, 12-bit color. Paste a screenshot of your result below, manage bit. So the worksheet tells you what you're supposed to do. Okay? You're going to get your answers by working through the code.org studio, but you're going to write them into your worksheet. Okay? Does that make sense to everyone? Lily, you look like this is oppressive.
Oh, no, I'm fine.
Okay, no, it is a little oppressive and it's all very new. So I expect questions, I expect problems, but I think we all have the basic idea and you have what you need. We're now done with class. Let me just poke through here. This is something that we'll go over next class, but it's the idea that digital images, when we create them, have a bunch of layers. They have the binary that controls the pixel layer. Then you have the sampling layer, and then you have the actual digital image. So it says digital displays a digital approximation based on sampling of analog. Oh, come on. Then samples of equal size are read from the analog image and assigned. Then each pixel is represented by levels of red, green, and blue light. Red, green, and the last one is red, green, and blue are represented with binary numbers. Things like that.
Did he just freeze for everyone?
Yeah.
Yeah.
Wow. Yep. Well. Okay, Lily, are you guys hanging out for questions or?
Oh, you were
You're done?
frozen.
All done.
I have one
Next-
question.
Sure. What's
Thank
up?
you.
Did you want us to do lesson 8 in it? The
Doing all day. What have you been doing?
No, he meant like the number 8 one with like the take a picture and replicate it.
Hang on. Which?
Like puzzle 8. Puzzle 8.
Hang on, let me back to here. No. Well, let's see if it works. Sorry about this. Hang on. Let's see if this bounces. Come on. Get me out of there. All right. So now, sorry. This sharing thing is really killing me these days. Go to desktop. All right. So if I'm in code.org, section 8. Okay. So this is the idea that you're just going to take a strip of this. If it's, this light blue, if it's here, maybe it's the yellow, you're going to take a strip and you're going to try and create an approximation of that in these pixels. It's not going to look like the other picture, but it's the idea you're going to make a couple different colors similar to what, this thing is. So it's either going to be light pink, darker pink, darker pink, dark pink, light blue, kind of lighter blue, red, reddish pink, orangish pink, reddish pink, orangish, or just variations. Some people are colorblind, and I forgot to bring that up. So the black and white images might be easier for them. Any other questions?
When is this due?
Monday, next class.
Okay.
Thank you.
Where do we
got it?
find step 3 on the worksheet? Because I went through the entire code.org lesson. I don't know where we're supposed to do step 3. Something about 12-bit
Step 3 is
color.
just the first one. So it's right here. Here's 2 RGB color.
No, on the worksheet you gave us.
Oh,
Step 3 in the worksheet.
hang on. Let me go to the worksheet. So 3 color bit. How to use the pixelation to fill in the last 2 pixels.
No, step 3. It says step 3, 12-bit color. Can you scroll down?
3 one. Oh, this is the 8-bit, 12-bit
Yeah, I don't know
color.
where we're supposed to find that.
You got to be in your
It's
we
not
never
on the
got-
lesson.
Okay. I would not worry about that. I am sorry, and I'll probably send out a note. I think this is part of the idea that see how this sheet is geared to last year's lesson. It says it's unit 2 in lesson 4.
Yeah.
I think they took out the 12-bit color item.
Oh, okay.
I don't
Okay.
think, because we never got to 12 bits, right? We went through everything in there.
Yeah.
It gave us 9-bit and 6-bit.
Yeah, we never did the
Right?
12 bits.
We never got to 12-bit.
Okay, so should I just
Okay,
like
so
turn
that's
it
great.
without the 12 bit?
Perfect. No, I'll double check with my teammates, but I'll send out an email saying that. Great observation. Thank you. It's just part of this crazy world we're living in.
Okay, thank you.
Good observation, Richard. Have a great day.